Well, thank you so much to the organizers for having me here today. I'm going to talk about something that is perhaps a slightly unusual seismic source, but I'm going to talk you through the work that has led up to us using seismology, seismoacoustics to track and characterize re-entering space debris. And I'll talk you through sort of some of the basics of atmospheric seismology. I realize it's probably a field that we all know something intuitively about just from hearing sounds in nature, but it's also something that we don't tend to think of very much as seismologists. So just a little bit about me to get started. Thank you, Will, for that introduction. But you may have guessed from my accent that I am British. So I grew up in Birmingham, which you may know as the home of Peaky Blinders. I did my undergrad at Imperial College London, so I was a physicist by training, but have since moved over into the world of geophysics. After my undergrad, I moved to Oxford for my PhD. So the Harry Potter staircase, as you might see there, was literally next to my office. After I finished my PhD, I actually went off and joined the Navy for a little bit. So that was a very different, very interesting experience to academia. And since then, I've moved out to Baltimore, which is where I am at the moment, doing a postdoc at Johns Hopkins University. And as Will mentioned, I'll be moving to Los Alamos in a few months. So if any of you find yourself out in the desert in New Mexico, please do stop by and say hi. So my journey sort of as a physicist, I got into geophysics. I often tell people I've never taken a seismology class, so apologies if I get anything wrong. But I ended up starting my work looking at seismic modeling, so solving the forward problem for systems, that Earth system, the Mars system, where we were including the ocean and the atmosphere. So regimes of physics that are very relevant here on Earth, where we've got both an ocean and an atmosphere, but are very often neglected because for the vast majority of seismologists, they don't have a direct impact on the results that we're trying to observe. The discipline of atmospheric seismology, as it were, despite being maybe a little bit foreign to many of us, is actually pretty old. So I sort of pick as a convenient starting point for the study or the sort of modern scientific study of waves in the atmosphere from seismic or seismic-like sources, the eruption of Krakatoa in Indonesia in 1883. So modern seismology, modern seismometers did not really exist at this time, but the explosion of Krakatoa was one of the loudest sounds ever produced. It was recorded as a series of acoustic gravity waves on primitive barometers all the way on the other side of the world, and indeed in some cases having made one or more passages around the globe. So whilst this wasn't a direct measurement of waves in the Earth, though they almost certainly existed from this event, it kind of laid some of the foundations for starting to think about regional to teleseismic excitation of atmospheric waves, which of course couple both into and out of the ground, and to link those to sources that are of interest and relevance from a societal perspective as well. The next sort of big relevant event that I like to link my work to is this image here. It's pretty grainy, pretty blurry, but hopefully you can see that it is an image of what was once a forest that has been completely leveled. There's a few trees growing back because this event took place just before the First World War, and this image was only taken after the Russian Revolution. It was in a very remote part of Siberia, so in the intervening 10 or so years, some of the trees have started to grow back. But what you're looking at here is a subsampling of several thousand square miles of forest, which were completely flattened by an event. What that event was not entirely clear at the time, though when the first Russian scientists reached the site about 10 years later, they noticed that all the trees were pointing away from what appeared to be a specific location. As it turned out, the shockwaves from this event were again recorded on barometers and as well on some of the first sort of primitive seismometers, which were then being deployed, especially in Western Europe. And what this event probably was a small impactor, maybe let's say about the size of a room, a small room, something like that, which exploded in the atmosphere, a fragment of an asteroid that didn't survive passage down to the Earth's surface, but exploded in the atmosphere and leveled these thousands of square kilometers of forest, basically stripping all the vegetation away from that shockwave that was produced by the exploding object. Thankfully, it doesn't appear that anyone was hurt. In fact, very few people even saw this happen. It was in a truly remote part of Russia. But if this event had happened only 2 hours earlier, it's at almost exactly the same latitude as Moscow. So this explosion would have taken place over the Russian capital. You can imagine the amount of damage, the number of casualties that would have been caused by something like that occurring over a metropolitan center. And those seismic readings are really one of the only ways we have of studying this event, at least in its real-time consequences, because there was no regional or even local instrumentation around there. We're looking at recordings that were made many thousands of miles away. One of the next big steps in atmospheric seismology was, of course, the advent of nuclear testing. So this image here that you're looking at was taken in 1946. It's the first shot of Operation Crossroads carried out in the Marshall Islands. This is Bikini Atoll here. And famously, this site was a home of many US nuclear tests. This one you can see they were testing the effects of an underwater explosion against battleships. You can see part of the German and Japanese fleets anchored there that were then vaporized. In fact, that little black smudge in that column there is actually a vaporized battleship, probably the USS Arkansas. And you'll also see there sort of looks like there's a disturbance propagating out across the water. It's a sort of faint white line just below the battleships. And what that is a shock wave. It is a non-linear sound wave. And what you're looking at is the intersection of that sound wave with the surface of the water. If you play this video forwards in time, or the series of images forwards in time, you'll see that shockwave hit the land. It blows over many of the trees. You see they've been painted so that this can all be studied from remote footage. But that shockwave both couples into the atmosphere, and energy propagates as acoustic waves around the globe. It also couples into the water and also couples down into the solid earth, where those waves will propagate as seismic waves. And you might wonder, why is this of interest? Why is this of relevance? Well, acoustic and seismic detections in the 1950s formed the backbone of nuclear monitoring because it was recognized that it was very easy for nations to carry out potentially illicit nuclear tests, especially at sea. And so atmospheric seismology became a way of tracking and monitoring the signatures from said explosions. Famously, Edward Teller, the inventor of the hydrogen bomb, he was not at the test of the first US thermonuclear weapon, but he knew from sitting in his basement in California when the explosion had gone off, because a few seconds later, or a few minutes later, he saw his seismometer displaying a signal that was entirely consistent with a nuclear explosion. Today, even though we have instrumentation all around the world, cameras, radar, seismic, hydrophones, acoustic, atmospheric sort of recordings of seismic events are still very, very valuable. So some of you might recognize this picture. It was taken in 2013. What we're looking at here is another bolide exploding over the city of Chelyabinsk in Russia. Again, this event was, something that exploded entirely in the atmosphere. It doesn't seem like anything at all reached the ground, but the explosion of this object, which was probably about the size of a car, created a shockwave that caused about $30 million worth of damage and injured thousands of people, primarily from blown out windows. Again, the seismic recordings from that event and the acoustic recordings from that event allow us to study the properties of that bolide, even though there was relatively limited instrumentation there on the ground at the time. From those seismic recordings, we can make estimations of, say, yield, of direction of travel, of velocity. From that, we can figure out where in the solar system this object was coming from. We can figure out how much damage it would have done if it had occurred, say, 10 kilometers higher or 10 kilometers lower. So really taking signals which we wouldn't necessarily imagine seismometers and infrasound sensors are sensitive to, and using them to study these problems, which are very relevant as a sort of natural hazard that we don't often think about. These sorts of things are comparatively rare, but when they do occur, they are incredibly destructive. I just want to touch briefly because it's kind of cool, and it was the first project I got to work on that was sort of my own thing during my PhD. I was very lucky to be a member of the science team for NASA's InSight mission to Mars. And on Mars, all of those processes that I've just talked about are relevant, and in some ways even more relevant, because Mars has a very thin atmosphere. It's closer to the asteroid belt. The flux of impactors striking the surface is even higher. And so not only can we study the properties of, say, the properties of small bodies in the solar system, not only can we study impact processes using the seismic and acoustic waves produced by impact events, we can also use them as sources that we have a constrained timing, a constrained location for. And that's really valuable for lifting many of those degeneracies we have in the inverse problem when we're working with stations where we basically have three components on a single location and nothing more. Just to give you an example of what a seismogram from Mars looks like, because I realize many people might not have seen one before, this is an event that occurred on Christmas Eve in 2021. I actually got the email from this during Christmas holidays. Very keen to leave it all behind and wish it hadn't happened. But of course, upon looking at it, I realized that this is something very unusual. So it is a Mars seismogram, which has clear seismic phases, both of body waves and surface waves. That in and of itself is quite rare. You'll also notice it lasts for more than an hour, which by Earth standards is kind of ridiculous. And as it turns out, this event here was actually associated with the formation of the largest fresh crater we have ever seen form anywhere in the solar system. It's 150 meters across. The blast zone is around 60 kilometers across. So you could put this at the center of any major city, and it would basically cover, the central square or something. The blast zone would cover the entire metropolitan area. And the seismic recordings from this event not only allow us to study the dynamics of those impact processes, they allow us to explore some of the subsurface properties. You'll see some subsurface ice that's been thrown out by the crater there, and also to really probe the interior structure of Mars in a way that would not otherwise have been possible without these sources where we knew exactly when and where they'd occurred and how big they were. So you're probably wondering, how does this all link to space debris? And it's a bit of a convoluted story, but in many ways, it's what I think is the cool bit about this, that we went from something that we were doing for planetary science applications and then stumbled upon a way that we could apply it to Earth. So it's one of those brilliant use cases that showcases why this research was so relevant. And the kind of linchpin in all of this was another planetary science mission, which I'll mention in a second. But the motivation for this work was that we had all these wonderful signals of the meteoroid exploding over Chelyabinsk, of these impacts here on Mars, some of which we got acoustic waves from as well. But the trouble was we didn't have any independent ways of calibrating those measurements. For this event here, we see seismograms which have a velocity peak amplitude of somewhere around 20 nanometers per second. What does that really mean? Okay, well, we can link it to the size of the crater, but how do we calibrate for things like the speed of the incoming projectile, the mass of the incoming projectile, the angle of entry, and so on and so forth? And one of the great difficulties is that all of these processes, these re-entry processes, they happen very fast. They take fractions of a second to form the crater. The objects are going off in tens, if not hundreds of kilometers per second. We don't often have, artificial calibration targets that we can work with that are at anything close to those speeds. So one of the links that we came up with was the re-entry of the Osiris-Rex spacecraft. So some of you may know Osiris-Rex was a sample return mission that NASA ran to the asteroid Bennu. And one of the really exciting things about this mission is that it brought some of that sample back to Earth. But not only did it bring it back to Earth, it brought it back to Earth from interplanetary space. And that meant it was going at interplanetary speed, so upwards of about 11 kilometers a second. That's about 42,000 kilometers per hour. That's far faster than, things like missile re-entries, like the space shuttle re-entry, and starts to approach the speeds of these natural meteoroids as they enter the Earth's atmosphere from elsewhere in the solar system. And so this was an excellent calibration target because we knew well in advance of this happening, exactly when and where Osiris-Rex would be entering the atmosphere. We could prepare the instrumentation to listen for it, and we knew how big it would be, we knew what its mass would be, so we could make all of those calibration measurements that are otherwise impossible at these kinds of speeds. So this re-entry happened in 2021. That's me out in the field preparing for it. I don't often get to show fieldwork photos as a planetary seismologist, so I like to chuck this one in here. But you can see we're out in sort of the Great Basin Desert in Nevada. There's very little around. And it's an excellent place to do this sort of work. It was relatively flat, other than the mountains you see in the background, and we could set out the instrumentation exactly how we wanted to try and collect and characterize the shockwaves from the spacecraft re-entering the atmosphere and make all of those calibration measurements. So this is a little schematic of the spacecraft's trajectory. The top panel, you'll see a vertical profile, a side-on profile, and the bottom panel, you'll see the top-down profile. So those red triangles are showing you the seismic array. You'll see that we laid it out such that the long arm was parallel to the trajectory of the re-entry, and the short arms perpendicular to the trajectory of the re-entry. So that gives us some really nice measurements of the slowness of the wave across both axes. So the re-entry path, the atmospheric interface, which is the point that we define the atmosphere as having enough density that things like sonic booms, like shock waves, molecular drag start to become important. It's about 132 kilometers in altitude. In this case, it's just off the coast of San Francisco in California. So at this point, the spacecraft hits the top of the atmosphere. It's going about 43,000 kilometers per hour. It passes almost directly over downtown San Francisco. I did ask some friends to go have a look. I don't think any of them saw it, unfortunately. But it crosses California in about 20 seconds. So it's going pretty fast. At that altitude, the atmospheric drag is not really slowing it down. Over Nevada, though, you can imagine the atmospheric drag is increasing near exponentially as the atmosphere gets thicker and this capsule is descending. Around 60 kilometers in altitude is where we have a maxima in the combination of velocity and atmospheric density that gives us the strongest production of sonic booms. So that's that red dot that you can see just to the west of Eureka, Nevada. At that point, the spacecraft's heat shield is about 2,000 degrees centigrade, and it's pulling about 300 meters per second squared of acceleration. So about 30 times g. And all of that energy is being bled off into the atmosphere, and a large amount of it is going into producing that sonic boom. From that point on, the spacecraft rapidly becomes subsonic, and the landing is just outside Salt Lake City. That whole re-entry sequence, it's about 600 or 700 miles long. It takes on the order of 10 minutes to go from 43,000 kilometers an hour to stationary, all of that energy being bled off into the atmosphere. And so that's really what we wanted to measure are the shock waves from this event. And I'll give you a second to look at them here while I grab some water, but I think they're in some ways some of the most beautiful seismograms I've ever seen. So the top panel, you're looking at the shock wave in the direction along the array. In the bottom panel, you're looking at the shock wave in the direction perpendicular to the array. And you'll see this very characteristic, what we call an N-wave shape. So this shock wave is very much a discontinuity in the physical properties of the air at the wavefront. It decays over time, but it maintains this character where you basically have nothing, and then a very, very sharp, near instantaneous compression, followed by a rarefaction, so that's the up and down. And then, there's a bit of mess in the coda, which is normally a combination of slower linear acoustic waves, of waves which have coupled into the ground and excited either Rayleigh or Love waves. And then, of course, sort of the distributed strain on the surface will produce long period effects. So, for example, rotating the seismometer about its center of mass as well. But you can see very clearly that difference in slowness in the two axes, which we can use to study not just the velocity of the object, not just to recover its size, but to make some really precise measurements of its trajectory. So this is a beam pack, which was done by colleague Tim Craig at the University of Leeds. And what you can see there in the vertical direction, we've sort of projected that beam back in, you can look at the slowness. It comes out in the y direction at about 0.05 seconds per kilometer, in the x direction about 0.2 seconds per kilometer. And from that, we can work out that the spacecraft was either on or ever so slightly to the north of its nominal trajectory. So not only can we make some measurements of the direction of that trajectory, we can compare what happened to what we expect to happen given the nominal re-entry profile. And that's particularly valuable for this event. You may recall, if you watched the landing, things didn't exactly go to plan. One of the supersonic parachutes failed to open. As a consequence of that, a lot of the assets failed to capture, so the airborne assets, the chase planes, failed to capture the imagery that they wanted from this. So the seismic and acoustic data are a really valuable way of capturing and sort of validating what we think happened during re-entry, because a lot of the measurements that we otherwise intended to make were lost. In the right-hand side, you can see the stack of those signals. You'll see that when you stack them coherently, the overpressure, that's the compression to start with, is actually much stronger than the rarefaction. That's quite common for nonlinear shock waves. It reflects some of the dynamics of sort of relaxation of air. And we can go even further. We can sort of pick a station, look at that either in the stack or individually, and make very precise measurements of the duration of that shock wave. And for this event, we come out with a shockwave duration of about 0.18 seconds. The theoretical model for shockwave propagation, given a speed and a size of commensurate to Osiris-Rex, suggests that we should get about 0.16 to 0.17 seconds. So in this case, we were able to very precisely validate our model for how the duration of the shockwave should relate to the object's size, altitude, Mach number, cross-sectional area. And of course, that's great as a calibration, but it also means if we have objects where we can measure the speed, we can measure the altitude, but what we're really not sure about is the size, because we don't know how big many of these meteoroids are, we can start to make inferences about how big they were as well. And from that, we can tell something about material properties and strength. That tells us something about what kind of impactor was it? Was it asteroidal? Was it cometary? Was it, as I'll talk about in a second, tongue-in-cheek an alien spacecraft? What was it exactly? And we validated the scaling relationship for duration very, very well. Ironically, the other scaling relationship which we tested for was pressure. And it turns out the overpressure relations that we work with are entirely inaccurate. They predict an overpressure of about 20 pascals. We saw less than 1. So this is the first time I think any of these relations have been validated any more than about Mach 5. Here we were able to show that the duration one, we can push all the way out to Mach 30 and use to characterize sources. But for whatever reason, probably due to the hypersonic dynamics, the pressure scaling relation really isn't appropriate. So that's hopefully a little bit of an introduction to the concept of what I call atmospheric seismology, seismoacoustics. The bit that you're probably all here to learn about is the space debris. How is this relevant? Why is this relevant? And so I kind of, I don't often give a chronological talk, but I was on Twitter back in the day when we still all used Twitter, and someone posted this picture. And, they were like 1 o'clock in the morning in Los Angeles. People have seen these bright lights streaking overhead. And, weird things happen in LA, not infrequently. I'll give you that. But this is pretty unusual. And people are understandably worried. Has a plane exploded in the sky? Has someone launched a ballistic missile? What are we looking at here? And the truth is, it wasn't immediately clear what this was. We knew that there was a piece of space debris which would probably enter the atmosphere sometime on the 2nd of April 2024, but there were 2 re-entry predictions. One was somewhere in the South Pacific, the other one was somewhere in the North Atlantic. So separated by about 20,000 kilometers, almost as far as you can get. No one was predicting anything unusual to happen in the skies over Los Angeles that night. Yet, here we were. It appeared that those predictions had been entirely wrong. As it turns out, it's very difficult to predict exactly when and where space debris will re-enter the atmosphere, because once you're in the lower thermosphere, below about 200 kilometers, the interactions with drag become both nonlinear and chaotic. But not only had there been no prediction, As it happens, many of the radar systems over the West Coast had been offline on the night this had happened. So there was no radar data showing and being able to track this, at least no civilian or unclassified radar data. So the question was, what data sets could we use to help, the many people who'd seen this all the way across from Santa Barbara, LA, out into Nevada, what was this that they were seeing? And I thought, hey, we're in Southern California. It's the spiritual home of seismology, if you like. Let's see if we can see it on the seismic network. And it turned out we could. And I'd never really thought about space debris, but once I started looking into it, you start to realize just how big a problem this is today. So these are news headlines that, what are we today, the 14th, 15th of January? All news headlines about space debris that I've just pulled off news sources from the last 2 weeks, just to give you a flavor of, how big this problem is today, because I hadn't actually realized that until we started doing the seismic analysis. So this here, as it turns out, Chinese Shenzhou 20 spacecraft was hit by a piece of space debris. It stranded some of the astronauts up there for a while, which is really not great. This here announcing that there was another near miss for Starlink. And you can see even some of the language that's involved in this is very charged. International pressure from the second world. I mean, certainly not language we would tend to use anymore, but people are very sensitive to this issue. And of course, people start to do the calculations of, what risk is being posed to, for example, aviation. It looks like, there are chances up to 20, 30% I was seeing of another incident like we saw last year of space debris entering controlled airspace in an unpredicted and dangerous manner. As it turns out, the sort of worst space debris incident in history really showcases why we have a problem here. So this is the reentry of Cosmos 954 in the spring of 1978. It sort of spread debris all across the Northwest Territories in Canada, from Yellowknife all the way up to Baker Lake. The thing was, this spacecraft actually had on board a fully fledged nuclear reactor. And those fragments were scattered all across northern Canada. There was a huge operation to recover them. Not all of them were found. And part of the problem was it was, and it still is, incredibly difficult to track space debris once it is actively re-entering and burning up in the atmosphere. It's easy enough to track it once it's in space. Sometimes you can find it when it's on the ground, but the bit in the middle is really, really tricky. It was a problem in 1978, and it's still a problem today. So I thought, this event, Southern California, big seismic network, we know what the object is now. It's the orbital module from the Shenzhou 15 spacecraft. So Chinese spacecraft, it was left in orbit once it had completed its mission in a decaying orbit, inclined 52 degrees to the equator. So overflying everything from Melbourne to London on a very regular basis, most of the world's population there, all exposed to some increased risk. And the predictions we had got it completely wrong for when and where it was going to re-enter. So I thought, did we see anything on the seismic network? And not only did we just see a something, we saw signals on 125 seismometers across Southern California and Nevada. So in the top panel, I've plotted time against delay. It's a bit of a weird plot as a seismologist, but nothing else really lines up because, of course, this signal is not just a point source or a fault source. It is a line, and we are getting a continuous shockwave generation along that line. So you can see there's multiple stations, all of which have different characters. The two red lines are the first and last stations immediately under the trajectory. The rest of the black and gray lines are stations that are either intermediate between those or further afield, so not under the trajectory, but still picking up the shockwave. The first line, so SMI, some of you might know that station's in San Miguel Island, Channel Islands. It's a very clean shockwave like the one that I showed you previously, straight down, compression, straight up, rarefaction, short coda, and back to zero. SEV, it's in Sells Valley, so much further inland in California, much more complicated shockwave. It looks like there are actually multiple shockwaves there as well as a complex coda. And that's indicative, we think, probably of acoustic multipathing, of coupling into the ground, but also crucially fragmentation. So the spacecraft is breaking up, the components are not all traveling at the same speed anymore because they have different cross-sectional areas, different ballistic coefficients, and so we're getting multiple spatially separated shockwaves. You'll see as well that the character of those sonic booms recorded really varies across California. If you look at the ones between the two red lines, they're kind of compressed together, but you'll see they are all very long. Especially in the LA basin, we have this long coupling into the sort of sediments, which makes the signals very different in character to those around, say, 150 or 200 seconds of delay. Once we're out towards the Sierras, we're looking at rock that is, far less compressive, so the compliance is far smaller, and so we get very different characters of shockwaves. That's something we have to account for when we do this analysis. And so we went through and we picked those shockwave arrival times, and at this point I sort of put in my AGU abstract, and there's this nagging thought at the back of my mind: am I that idiot seismologist who has claimed to see space debris, but all they've done is found an earthquake in California? Because someone told me they have a lot of those there. But I plotted up the arrivals on the map, and it really is quite beautiful. So we're looking again at a map of Southern California all the way out to Nevada here. Each dot is a seismic station. It is color-coded with the time delay relative to the first arrival at San Miguel Island. And even without doing any fancy analysis, even without having to do any array processing, I think the pattern is pretty obvious. So first arrivals at San Miguel Island in a direction along a line from Santa Barbara to Las Vegas. The arrivals increase very quickly in time. So it sort of crosses the line between Santa Barbara and Las Vegas in 100 seconds or so. Perpendicular to that line, so sort of between Los Angeles and Bakersfield, you'll see it's much slower. We're looking at time delays of hundreds of seconds. And that immediately tells us something about what direction this object was going in. This paper should hopefully be out soon, and what we did in there is we animated and sort of contoured these arrivals. So hopefully this is playing and you can see that, but each of those is a contour of equal arrival time. I will play it again for you there. A contour of equal arrival time of the sonic boom at those stations. And then that gray line there that we've plotted, it's a little bit easier to see here. That gray solid line there that we've plotted is the best fit seismic line. So we fit the minimum gradient in arrival times, which maps to the trajectory. That dash line there is the radar prediction of what would happen if you just propagated the object's orbit down to the Earth's surface without accounting for drag. And I love this plot. I think it's definitely the prettiest seismic plot I've ever made. You can see that really cool move out pattern in the direction along the trajectory. The sonic booms arrive almost simultaneously across hundreds of miles because the object is going so fast. Perpendicular to that, the signals propagate much slower. They're propagating more or less at the speed of sound. You'll also notice that the contours are not equally spaced, so the 50 and 75-second contours are very far apart versus the 150 and 175-second contours, which are very close together. That's encoding information about the source altitude. As it turns out, the altitude determination is actually difficult because there's basically no slowness resolution for altitude under the trajectory line. There's good absolute propagation arrival time sensitivity. So if you imagine that the time it takes to propagate from 100 kilometers to the ground is obviously sensitive to altitude. The problem is the relative arrival times between different stations are largely insensitive to altitude because that angular change in elevation is so small. However, we can still, for example, work out stuff like the descent angle. So by comparing the shape of those contours that encodes information about the speed of the object to the slowness move out, we can derive a descent angle of about 1 degree. And that's great. That's about what we expect, but I think it's the first time it's ever been validated. So to understand how steeply the space debris is entering the atmosphere in a method such as this. You can also use a bit of a Monte Carlo approach to compute the uncertainty. So we can take our picks, add in random noise to them, and recompute how sensitive that trajectory is to the noise. You can see the 2 sigma uncertainty interval there. It looks substantially offset from the nominal trajectory line. Some of that difference is probably due to wind, but not all of it. And so again, we're validating that we really need to be able to track this debris in the atmosphere to figure out where any fragments, if any survived re-entry, may have landed. That difference of 30 to 40 kilometers, even if we can understand some of that uncertainty due to wind, that difference is enough that if you were looking for fragments, you probably wouldn't find any if you were basing your analysis just on the radar prediction alone. A really brilliant piece of work done by my colleague Konstantinos Charalambous at Imperial College London in this paper as well was to understand the fragmentation pattern that's encoded into this data as well. So I showed you those sonic booms. As it turns out, there's actually some signals in there which are not just the signal of the sonic boom, not just that N wave. There are clusters of stations which show coherent arrivals. And within those clusters, those arrivals are coherent. Further afield, different clusters don't show that pattern. And what we're interpreting those coherent arrivals, you can see one of the phase-weighted stacks as the dark black line in the inset panel. Those arrivals probably correspond to individual fragmentation events during re-entry. So as you imagine this object is entering the atmosphere, every now and then a piece will fall off or fail explosively, and that process isn't random. The weakest components fail first, that's normally the solar panels. The most solid components, sort of the main spot of the spacecraft bus, probably survive a lot longer. The densest, highest ballistic coefficient things, which unfortunately are often also the most toxic, so that's fuel tanks, battery packs, in some cases the reactor core, if it's got a nuclear reactor on board, though thankfully that's relatively rare, those things survive the longest. And so what we did is we looked at how is the energy distributed between those different fragmentation events. And that's that curve you can see there in the top panel. If we plot the relative fragmentation energy against the rank, so looking at this cascading process from a sort of system point of view, we see this really interesting line which has a clear slope of about -1. And what this indicates to us, it sort of validates that this isn't a single explosive failure. It's not that the spacecraft just explodes and all the components have disintegrated. It's also not that the spacecraft is slowly ablating the same way Osiris-Rex did, where little bits are breaking off over time. We see here is components explosively failing as they enter that hypersonic airflow. Some of them, they fail high up, some fail lower. Those bits that are broken off then fail in sequence, and it gives you this cascading multiplicative failure, which, to us indicates that the failure is probably governed by a combination of the internal stress dynamics within the spacecraft bus and that interaction with the airflow. So if we're thinking about what might survive to the ground, this sort of analysis is really valuable. And of course, one of the other unfortunate conclusions is if you're looking for debris, probably a multiplicative cascading failure is the worst sort of failure from a environment and ecology point of view. It's not that we have a single explosion where everything disintegrates and all the fragments are gone. It's not that we have a slow ablation where most of the spacecraft makes it to the surface in one piece. We kind of have the worst of both worlds, where some components break off early and then explode, and some make it far lower into the atmosphere. So the debris, we think, is being sort of created along what's quite a compact breakup zone laterally. It is quite a narrow cylinder, but it is significantly extended in space. And that is a big problem if we're thinking about debris recovery efforts. I just want to touch briefly on a little bit of work that we've done with some colleagues at Caltech who very kindly gave us access to a distributed acoustic sensor. So this is the Ridgecrest fiber, which also picked up this event. And the really exciting thing that we're working on now with this event, which we weren't really able to do with the seismic data as well as I'd like to, is constrain the altitude. And the reason for that is that, as I mentioned, the seismic stations don't tend to be very sensitive to altitude. And also, even if we interpolate, it's still many acoustic wavelengths between stations. So that slowness resolution really isn't great because we're assuming coherence over a length that it probably doesn't exist. With DAS, that isn't a problem, and suddenly we have thousands of channels which we can make automated picks on. So if you're not familiar with DAS, each vertical line is a channel, each of those black messy lines is a car, and those blue dots are plots of sort of an automated pick where I put on that very nicely and easily identifies the first arrivals. And from that, we can start to do the sorts of slowness calculations that allow us to make much more detailed measurements of the source altitude. Just to reassure you that this doesn't require you to be in Southern California to work, which is, of course, a legitimate concern. It's one of the most dense, if not the densest instrumented area in the world. We've also been able to make some really useful measurements far further afield in far more remote areas. So some of you will have seen that Elon Musk's starships, they had several consecutive failures in the spring of last year. And many of those happened over the Caribbean. We had, the Turks and Caicos Islands, British overseas territory, people seeing these strange lights in the sky, hearing enormous noises, and then all of a sudden debris is raining down on them. The seismic data can actually give us some insight into that process as well. So what we're looking at, the top panel and the bottom panel are from Starship 7, the middle panel is from Starship 8, top one's the Turks and Caicos Islands, the bottom one is Cayveres in Cuba. Signal at Cuba looks reasonably much like what we would expect. It's a shockwave. It's pretty clean, probably associated with a sonic boom from debris that is still reasonably compact in its re-entry. It's producing a single sonic boom. The other event, it looks unlike any sonic boom seismogram I have ever seen before. In fact, the closest match for what I could say this was probably thunder. If I didn't know that this event lined up exactly in time with the re-entry and the reports of the sounds that people heard, you'd probably, conceivably pick seismic phases on there and say it was an earthquake, but it's not. What it is a 200-second long sonic boom and audible rumble that is caused by the re-entry basically happening directly overhead. And so not only do you have that sonic boom propagating down to you, you have a cone of energy propagating down to the ground from all of these different fragments re-entering the atmosphere, producing separate shock waves, and of course then exploding. So if you look at the peak ground velocity, we're looking up to 30 microns per second here. That's enormous for a source this size. And, I didn't hear this, obviously, but I can imagine if you didn't know what it was probably pretty terrifying to hear. So even where we only have 1 or 2 stations recording the sonic booms from this debris, we can still make really useful inferences about the nature of the source process. And of course, our ultimate question is how much risk did it pose and did those fragments reach the ground? And that's this question that we're sort of working towards now, is trying to understand and go from, hey, someone's seen a bright light, was it space debris, to analyzing seismic and acoustic data in as close to an automated pipeline as we can get, deriving trajectories and re-entry angles, and then answering that kind of golden question for us which is, did stuff reach the ground? And if so, where did it fall? So the last thing I'd like to talk to you about today is a little bit of a fun project, which was relating to something which may or may not have been alien space debris. Now, some of you are probably wondering what exactly you've signed up for in today's talk, because you weren't expecting aliens to appear. But as it turns out, other people seem to think they are around. So you may have seen the study that came out a few years ago where a team from Harvard had claimed to find some alien space technology at the bottom of the Pacific Ocean. Very interesting result. Now, I read this with curiosity, and I only really became professionally interested in it when I read that the way that they had located this space debris on the bottom of the seafloor is they had recorded the sonic boom from the space debris supposedly re-entering the atmosphere on a single station, or 2 stations they claim. They'd used that to find an exact location to within 100 meters, and had then gone down to the bottom of the Pacific with a remote operated vehicle and recovered a bunch of that debris. So this is the location that we're talking about here. So those 2 green crosses are the location that they'd looked for. There was indeed a meteor. There's no questioning there was a meteor indeed. That's the trajectory is the pink arrow there. The question was, did this meteor come from interstellar space, or was it just an ordinary solar system meteor? And was it or was it not a piece of alien space debris? And so they had claimed a detection at this station, AU Manus, that's an OSPAS seismic station on Manus Island. And this was the mechanism that they proposed. And this is a very physicist thing, I accept, to take a seismogram and plot it as a histogram. It's clearly something a seismologist wouldn't do, but there you have it. And they said that they'd seen 3 distinct peaks in that seismogram, maybe, but they sort of linked those to a direct air wave, and then the sonic boom coupling off the water back up to the seismometer, and that can happen, but maybe not in this manner. So I thought, they've done that. Let's go look at the sonic boom supposedly from this space debris. And this is the signal they called out. So the green line is the fiable origin time, and then the purple line is the pick that they've made. So that's the same signal I just showed you, plotted in 3 components here and not as a histogram. And so the question is, of course, could this be a sonic boom? Is that a sonic boom from a piece of re-entering alien space debris this time? And to answer that question, we had some really great analysis with a team at Imperial, a team at the CTBCO, and at Columbia. And the first thing we did is to look at how many signals like that there were. And it turns out there are many over the course of a day. So potentially many pieces of alien space debris re-entering the atmosphere on a semi-regular basis. The very strange thing is that these signatures appear to show a correlation with local time of day. So there are far more of them occurring between about 6 a.m. local time and 10 p.m. local time. Now, I'll give you that. It's clearly not an earthquake, because as far as we know, they don't tend to show that sort of diurnal variation. But, aliens, not sure what they're looking for. Maybe they prefer to arrive during daylight hours. So the next thing we did to analyze this space debris signal is we looked at the polarization of that signal to try and give us some idea of the azimuth. And so they picked sort of one of those pulses, the one on the right, and we looked at both the one on the right and the one on the left. And it looked like a source that started off at a southerly azimuth, maybe a little bit to the southwest, trended north, stopped for a little bit, started again at the same azimuth, and then trended south again. And so when you plot up the location of the seismometer, it's really not in the best site. It's close to a number of major sort of buildings and so on. And so the question was, is there anything on this site which might follow the same sorts of patterns that we're seeing in that azimuth derived from the signal? And as it turns out, the best match that we could find to the change in azimuth was not from a sonic boom. It was actually from the road between the highway and the naval base. So our conclusion, unfortunately, was that this particular piece of alien space debris was in fact a truck. And that truck was just an ordinary truck that maybe drove off the main road up to the hospital, dropped someone off, picked someone up, can't tell which from the seismic data, and then drove back again the other way. And so despite not really being a serious project in some sense, this piece of space debris analysis got far more attention than any of the other ones. It's the only time that I feel that both the New York Times, the Daily Mail, and the Washington Post will be all on my side, which was a very interesting exercise in understanding how some of the seismic data that we put out there as seismologists can both be used and misused to support conclusions on politically charged topics, shall we say. And if this story isn't quite over, I won't say too much more, but stay tuned for some additional quite cool analysis that we've done based both on the seismic data and some historical oceanography collections, which hopefully you'll be able to read about in a separate paper in the not too distant future. So thank you very much for listening. I hope all of you enjoyed that. Maybe it was a interesting diversion on a Thursday afternoon into understanding how we can use seismic and acoustic data to address and characterize and understand a problem which really is a new problem for society. It's something which is going to become literally exponentially more relevant over the next few years with the rise of satellite mega constellations, and poses an increasing risk to both life and infrastructure on the air and on the ground. And with that, I will end and invite, if you have a question, I'm more than happy to answer it, or at least try to. If you have thoughts or ideas about how we can take this analysis further, it really is something that is completely new, both to me and the field, I think, so I would love to hear from you. Thank you very much.